A catalyst is a substance that increases the rate of a chemical reaction without going through any permanent chemical change. So in this diagram, the blue line represents a reaction without a catalyst, and the pink line represents the same reaction with a catalyst. So as we can see, a catalyst allows the reaction to occur without needing as much activation energy. Catalysts can be divided into two main types, heterogeneous and homogeneous. So let's take a look at the differences between the two. So as we can see, a heterogeneous catalyst is in a different phase than its reactants. As we can see, all the reactants and products are gases, but the catalyst is a solid. And this makes the catalyst easier to separate from the reaction. But a homogeneous catalyst is in the same phase as its reactants. As we can see, they're all aqueous. And because they are in the same phase, the catalyst is extremely difficult to remove from the reaction. For heterogeneous catalysts, reactants stick to the surface of the catalyst at active sites, which makes the reactant molecules more reactive. For homogeneous catalysts, the catalyst provides a new reaction mechanism with a lower activation energy than the original mechanism. So a reaction mechanism is the sequence of steps by which a reaction occurs. Let's take a look at the reaction 2A plus B plus E equals F. Since this reaction cannot occur in one massive collision, the reaction must be broken into steps, called elementary steps. So the reaction mechanism for this reaction would be As we can see, there are some substances that are formed in one step and used up in a later step, and these are called reaction intermediates, and in this reaction, C and D are both reaction intermediates. As we can see, they were formed in one step and then used up in a later step. The elementary steps which occur at the slowest rate is known as the rate-determining step. A reaction cannot occur any faster than its rate-determining step. And as step 1 involves the most amount of molecules, since there are 3 molecules in this reaction, this step 1 is most likely to be the rate-determining step. So as we can see here, it's a little bit confusing, but we can see that this whole equation together is the reaction mechanisms, and step 1, 2, and 3 are elementary steps, and then C and D are reaction intermediates because they are created in one step and then used up in the next step, and step 1 is the rate-determining step because it is the slowest step. A potential energy diagram is a diagram used to show the change in potential energy of a system as reactants are converted into products. Let's take a look at a potential energy diagram for an exothermic reaction. The activation energy is the minimum amount of energy required for a reaction to occur. The activation energy for this diagram is 60 kilojoules. The activated complex is the arrangement of atoms that occur at the peak of the activation barrier. In this reaction, the activated complexes are structures A and C. The transitional state is the configuration of atoms at the local energy maximum. The transitional state for this graph is structure C at 60 kilojoules. The enthalpy, or delta H, is the amount of heat produced or absorbed in a reaction. In this graph, the enthalpy is negative 20 kilojoules. The collision theory is used to predict the rates of chemical reactions, and it explains why different reactions occur at different rates. The theory states that in order for a chemical reaction to occur, reacting particles must collide with one another, hence the name collision theory. There are four main factors of the collision theory in the overall speed of a reaction. The four main factors are concentration, surface area, temperature, and nature of reactants. All of these factors have an effect on the rate of reaction as they change the way the particles act. Let's take a closer look at how concentration affects the rate of reaction. The collision theory states that increasing the rate of one or more reactants will increase the rate of reaction, as this will lead to more collisions of that reactant in a specific time period. Now let's take a look at how surface area affects the rate of reaction. The collision theory states that increasing the surface area of a reactant will increase the number of particles available for collision, and therefore increases the number of collisions happening in a specific time period. Let's see how temperature affects the rate of reaction. The collision theory states that an increase in temperature will increase the rate of reaction, as adding heat will raise the kinetic energy of reactant molecules, meaning that more molecules will have enough energy for an effective collision. Now let's take a look at how the nature of the reactants affect the rate of reaction. There are four aspects of the nature of reactants: bond type, bond strength, number of bonds, and the state of reactants. According to the collision theory, for bond strength, molecules with stronger bonds will have a slower rate of reaction. For bond type, reactions with ionic bonds will have a slower rate of reaction, as ionic bonds are very strong compared to those of covalent bonds. So, reactions of covalent bonds will have a faster rate of reaction. For the number of bonds, the more bonds there are in the reaction, the slower the rate of reaction will be. For the state of reactants, solid reactants react much slower than reactants of liquids or gas.